All right. Let me talk about one particular problem, and then I may also address some other questions if you have any. If you can turn to page 8, this is number 16. Find the limit of one side of the limits of something that involved the piecewise function. So I want to present this a different way than the way that I worked out on the key. Whenever you see an absolute value function, it always feels a little bit cumbersome to work with absolute value functions. But let me just kind of talk about it from this perspective. Let's just look at that absolute value of x minus 2. Again, this is page 8, number 16. Absolute value of x minus 2 on its own would look something like this. Okay. Vertex is at 2, 0, and the graph just extends out in the V-shaped way. Now, absolute value of x minus 2 can be thought of this way. It can be broken down as just the combination of two linear functions that happen to have the same starting point or same ending point. So absolute value of x minus 2 is just this. It's just a positive slope version of the graph, which is just x minus 2. And this graph would continue if it weren't broken, if it weren't stopped. So this x minus 2 is only to the right of 2. Right? If we were to just graph x minus 2 and give it a starting point at 2, this is what would appear. This portion is the negative slope version of x minus 2. So if I do negative parentheses x minus 2, that would represent this negative slope version. And that is to the left of 2. Now, the point 2, 0 is also defined. It can be defined by either the x minus 2 or the negative x minus 2. It doesn't matter. So you can just put an equal sign under one of them and just let one of them define that point. Okay, but this is not the function, the problem that we're dealing with, right? It's also divided by x minus 2. But if we know that absolute value of x minus 2 is the combination of two piecewise, if I divide by x minus 2, then I'm now sitting at the function that I want. But if I divide this by x minus 2, I also need to divide these by x minus 2. Okay, so hang on with me for a second here. If I were to clean this up, or if I were to try to clean this up, what does x minus 2 over x minus 2 turn into? Just 1. Okay, so this is really just 1 to the right of 2. And this cleans up to be what? -1, right? These cancel out, only -1 remains. -1 x to the left of 2. So this is the same thing as this. And if I wanted to approach 2 from the left side of 2, that means I'm starting from the left, which is like 1.5, 1.6, 1.7, 1.8, 1.9. Those are all values that's less than 2. So any value that's less than 2, it's approaching -1. So that's why we have -1. Okay. So this is a good strategy for absolute value functions. Sometimes it's tough to understand, wait, what do I do with absolute value functions? Just know that you can always break it into two linear graphs. And once you're down to two linear graphs, it's a lot easier to interpret what's going on. So if we can get it down to this stage, then it's a lot easier to imagine the graph is just headed towards -1 from the right side of 2. Sorry, from the left side of 2. Okay, page 7 through 14. Are there any questions, any problems you want me to go over with you? Okay, if not, we're going to go to page 15. And we're going to talk about continuity and discontinuity. So this would be an example of a continuous function. A continuous function means that you can sketch the entire graph without ever having to lift up your pen or pencil. So this basically is a connected graph with no holes, with no asymptotes. This will be a continuous function. This, however, would be a discontinuous function because there's clearly a break that is going to force us. If we were to sketch this graph, we would have to sketch the graph, lift up our pen or pencil, and then move to the next part of the graph. So this would be considered a discontinuous function, where there are holes or asymptotes or breaks in the graph that is causing the graph to not be able to be drawn with just one stroke. Okay, we have a couple of types of discontinuity. So let me go through each of them. The first is if we have a hole in the graph where it's only 1 point away from being continuous, and we call that a removable discontinuity. So essentially a hole in the graph. And the second and third type are both non-removable discontinuity. And non-removable usually means we have to replace more than 1 point in order to get the graph to be continuous. So we have non-removable due to vertical asymptote. Like what we see here in the second graph. And then we also have non-removable due to jump discontinuity. And that's where we have one branch of the graph that stops and that picks up at a different point and then continues. So basically, a lot of times, the way that this is going to look function-wise, it's going to be a piecewise function with a break in between. For each function, identify the type of each discontinuity and where it's located. So if we can factor everything out, we know that whatever is going to cancel out between numerator and denominator will be a hole in the graph, and that would tell us that there's a removable discontinuity at that point. But if there's a vertical asymptote where there's a denominator expression that's not canceling out, then we know that there must be a non-removable discontinuity at that point. So for number one, we can factor and look for discontinuities. X minus 2, whatever cancels out, is telling us there's a hole at x equals 2. So we know there's a removable discontinuity at x equals 2. And then the x plus 5 is telling us that there is a vertical asymptote or a non-removable discontinuity at x equals -5. Can anyone tell me what the x minus 6 is telling us about the graph? X-intercept, yeah, it's a 0 of the graph. Yeah, x-intercept, 0 or a solution of the graph. But x minus 6 is not going to play a role in discontinuity. It's just a point on the graph that we're going to use quite a bit down the road. But right now, we're just focusing on the 2 and the -5. Okay. So we can say x equals 2 is a removable discontinuity. And x equals -5 is a vertical asymptote, a non-removable discontinuity. Okay, try number 2. See if you can factor all the way. Whatever denominator cancels out would be the location of the hole of the removable discontinuity. And any denominator factor that does not cancel out with a numerator would be where there's a vertical asymptote, will indicate to you where there's a vertical asymptote. So denominator can factor x to the 4th minus 1. That's the difference of squares. I can break that x to the 4th minus 1 to be x squared minus 1 and x squared plus 1. X squared plus 1, we can't factor that anymore. We could, but then we have to involve imaginary numbers, and we're not going to have any. We're not going to be working with imaginary units in this course. So the x squared plus 1 stays as it is, but the x squared minus 1 can be continued to be factored. X squared minus 1 becomes x plus 1, x minus 1. X plus 1 goes away, so we know there's a hole at -1, therefore a removable discontinuity. And at x equals 1 will be a non-removable discontinuity. There's not a discontinuity for x squared plus 1. Nothing. If I set that equal to 0, I'm not going to get a real number. So we can ignore that x squared plus 1. It's not going to cause it. It won't. There's no x values that will ever cause that to be 0. Fine. Okay, moving into a formal definition for continuity. Have you guys write this down? So we know that if a graph is going to be continuous, it just means that we can sketch through the graph without lifting our pen or pencil. It's easy to see, it's easy to recognize visually. But if we want to use the language of limits, we would need to kind of think of it as 3 components. We need 3 things to be true before we can confirm that the function is continuous at that point. So, but whenever we talk about continuity, we're always talking about continuity at a point. So we're not usually not talking about continuity for the entirety of the graph. We're usually just focusing at a point and asking, is this point continuous for this graph? So in order for a function to be continuous, 3 conditions must be met. The first condition is whatever point that we're referring to, and the problem is always going to indicate to you either directly or indirectly what point we're is in question. Okay. So you're never going to have to guess, wait, what point is this problem asking for me to involve? It'll always be directly stated, or there's going to be enough context clues where you're going to know what that C value is, what that point is. So f of C has to be defined, right? That point that we're talking about, first of all, has to be defined. And the second thing is the limit has to exist. So the graph has to connect towards the same point from both sides. And sometimes we can rely on just one statement. Other times we may need to rely on two different statements, especially if it's a piecewise function and we have two different functions defined. We have to look at each individual movement of the graph and see if they're actually moving towards the same y value. So this will be an example of where the second condition passes. Where the graph is clearly moving towards the same y value. This would pass the second condition. The third condition would be, now once you get to the third condition for continuity, you're not creating any more data. All you're doing is looking back at what you've gathered from 1 and 2 and asking yourselves, are they in agreement? Is the point that's defined the same as where the limit exists? If they are, then everything is one and the same, the graph is continuous. But if they're not, like this example, then the third statement would break down. The limit is at this point here, but the point is defined elsewhere. So if the point is not filling in the hole from the second statement, then the function would not be continuous, and the third statement would have to be indicated as false. We'll say, oh, the limit as x approaches c of f of x does not equal to f of c. Therefore, the function is not continuous at x equals c. But if the point is defined where the limit is, then all three conditions would pass. I put a hole there, but that hole is getting filled in by the point, so everything is connected. The point is there, the graph is moving towards the same y value, and the graph is going to be nice and continuous through that point. So let's look at example 1, where we're going to walk through our continuity conditions as we determine whether a point is continuous or not. I'm going to put this on a separate sheet just so I can have enough room, but we're just looking at number 1 below. All right, I'm just writing the conditions so we can have easy reference to it. This portion is especially useful or needed if we see a piecewise function involved. Usually if there's a piecewise function, we may have to involve this additional step to confirm that the second condition is either going to be true or not. Okay, here's number 1. Here's our function. Now, if we could see the graph, it'll be very easy to tell whether the graph is continuous at a singular point, because we can obviously tell by looking at the graph whether the graph is connected or not, but we're trying to determine continuity algebraically. So we don't have the picture in front of us. So we're using algebraic and limit notations to help us confirm whether the graph is connected at that point or not. So determine continuity for A will be at x equals -1. So we want to know, is the graph connected? Are these two branches going to actually connect at the same point, and is that point defined? So we're going to go through each of our conditions. So first, so we know that our C value is -1. So our first condition, f of -1. Does f of -1 exist? Okay, which piecewise would define it? X plus 2, yeah, because the less than or equal to, right? So we know this graph does define x at -1, so plug -1 in for x. -1 plus 2 is 1, so it passes the first condition, and we keep going. Right. Second condition, does the limit exist? Now you see that we have two piecewise functions that are defining, that are on either side of -1. We have a different function defined to the right of -1 versus a function to the left of -1. So because of the piecewise function, and we're split on either side of -1 with two graphs, we're going to have to rely on two one-sided limit. So it doesn't matter which one you do first. I'm just going to start with from the left of 2. So limit as x approaches 2 from the left side of 2. From the left, sorry, from the left side of -1, my bad. X value is -1, not 2. So from the left side of -1, we're talking about this function, right? Because this is to the left of -1. I would go ahead and write out that expression. So we're doing this piece of the definition. Okay. First, the one thing that we do, that we've learned, anytime we're evaluating a limit with a real number, we just plug in that -1. So plug -1 in for x. Don't worry about that one-sided limit. That's just notation for now. Plug in the -1, see what we get. We get 1 plus 2, which is 3. 3 plus 1 is equal to 4. So we know that from the left side of -1, the graph is headed towards 4. Now from the right side of -1, so we're trying to do this piece here. X approaching -1 from the right side of -1. That is referring to the second piecewise, because this graph is to the right of -1, headed towards -1. That's the x plus 2. So put x plus 2. Plug -1 in for x. I get -1 plus 2, which is 1. So from the right side of -1, the graph is headed towards a y value of 1. Is the limit going to exist? No. One's headed towards 4, the other's headed towards 1. The arrows are not pointing to the same y value. This would break down. If this breaks down, we know that we can't go to the third condition if the second condition fails, right? So now we know that our reasoning for the function not being continuous is because the one-side limits are not in agreement. And the way that you would write this, okay, you don't want to write it this way. 1 doesn't equal to 4. That's not going to be clear enough. You're going to write it this way. Limit as x approaches -1 from the left side of 1. You don't have to write out the entire expression. You can just call this f of x does not equal to the limit as x approaches -1 from the right side of -1 of f of x. You could write out these two individually if you want, but it's just easier to name those functions. But if you write the notation, make sure you name the function. You can't just leave it blank and say limit approaching 1 doesn't equal the limit approaching -1 from the right. You have to name that function. And this is enough for us to confirm that the function is not continuous at x equals -1. Okay, let's try part B. At x equals 2, that's our new c value. Again, you see 2 split on either defined for 2 different expressions. We're going to have to rely on one-side limits again when we get to it. But first condition, order pair. Okay. Which piecewise is 2 defined at? Second or third piecewise? Third, because there's an equal sign there. First condition passes. Second condition, we do have to rely on one-sided limit because we have 2 different functions defining either side of 2. Is this going to pass? Yes. So we can say, therefore, limit as x approaches 2 of f of x is equal to 4. Because the one-side limits are in agreement, we can just go ahead and you don't have to write out the limits is equal to each other. You can jump directly to the full limit statement and say that the limit as x approaches 2 is equal to 4. So that's the hard part. The hard part is trying to get through the first 2 conditions, especially the second condition. We keep going. The third condition. Now, once you reach the third condition, you're not creating any new data. You're just looking back at what you've gathered. Are we going to have an agreement between the first and second condition? Yes. So that hole that's created by the limit is getting filled in by that point. So everything is connected. Now, when we get to the third condition, I also want you to write it a certain way. I don't want you to say 4 is equal to 4, therefore function is continuous. I want you to write it this way. I want you to write f of 2 is equal to the limit as x approaches 2 of f of x. This is the way I want you to write it. Because the third condition is true, we can say, therefore, f of x is continuous at x equals 2. Okay, next page. I'm going to skip 1 and 2 because 1 and 2 are basically very similar to the ones that we've done. Let me talk about 3. Well, especially number 3, when there is like this unknown value that is given. Or we're trying to find this unknown value that will allow for the function to be continuous. So here's page 16, number 3. So this says, let f be the function defined by f of x. This is a piecewise function as well. It says, for what value of a is f continuous at x equals 6? But this piecewise function is different than the one that we saw before. The previous one that we saw had piecewise function with less than greater than. If you see less than greater than, you know you have two distinct branches that may or may not connect. Okay. If you see doesn't equal to, then an equal to, what this is really indicating to us is that everywhere except 6, the graph is connected. And then at A, x equals 6 is just a point. So this is a graph and a point. It's not a graph and a graph. It's just a graph and a point. So whenever you see x doesn't equal to 6, this means everywhere except 6. So that means to the left of 6 is defined by this expression. To the right of 6 is defined by this expression. It's only at 6 that it may be defined elsewhere. All right. So whenever you see this notation, typically there's no need for one-sided limit because you're not going to have two different functions defining the approach towards 6. It's the same function, so no need for one-sided limits. Whenever you see this notation piecewise, no need for one-sided limits. But if you see a less than greater than, then you typically need a one-sided limit because you have two different functions defining what's happening, what the movement towards 6. Now, we want continuity. So because we want continuity, all we're going to do is we're just going to step through our continuity conditions. And by the time we get to the end, we're going to be able to solve for A without even trying to. It's just going to naturally show up for us. Okay. So let me just show you what that looks like. So the first condition, we know the value, our C value is 6. We know the X value in question is at 6. So our first thing we need to find is find F of 6. F of 6 is equal to what? A. Okay, we don't know what A is, but eventually we're going to just come across it just by going through this continuity condition process that we have in front of us. Okay, second condition. Does the limit exist? We want to find the limit as x approaches 6. And we talked about how on the left side of 6 is this first function. To the right side of 6 is the same top function as well. We don't have to write two statements because we have the same function on either side of 6. All we need to do is just to write down that expression. Sorry, x minus 6. Okay, so now this is going to allow us to review our previous steps for evaluating limits. What's the first thing that we do? Direct substitution. Yeah, plug in 6. 36 minus 18 minus 18. What do we get? 0. Denominator, we get 0 as well. What does that tell us? Yeah, there's a what there? There's a hole, but the limit is going to exist. We just have to go through and find that limit. Okay, and we know that because there's a hole, there's something that is blocking access to us seeing that limit. So we're gonna have to find that factor that's causing it and remove it. So let's factor the numerator. Oops, sorry. We're minus 3 is minus 18, 6. Okay, what do we see? Yeah, cancels out. Reevaluate. What's our limit going to be? 9. Okay, so the limit exists. We keep going. The third condition, and we want all these to pass. So what will it require for us to pass the third condition? F of 6 must be equal to 9. Therefore, A must be equal to what? 9. So once we have our solution, we can stop. So here, we're using the continuity conditions to help us solve our missing value. But it doesn't take any extra effort. We just have to go through our conditions And by the time we reach the end of it, we're going to have our solution. Okay, let's try number 5. Number 5, virtually the exact same step as number 3. I just wanted to see if you can walk through it on your own and have it make sense on your own. Okay, so try number 5. If you can do one on your own, then you should feel good about this process. But be sure you provide all the notations that we went through with number 3. Keep all those notations in place as you work through number 5. Again, whenever you see a piecewise function with does not equal to and equal to, understand that there's a graph and a point in question, and there is no need for one-sided limit. All you need is just a limit statement for the function that's defining both sides of that target point. And if you get done with 5, try number 6 as well. Okay, your homework tonight, continue with your packet, page 15 through 19 all. And we're still on track to be able to finish all of our new content by Friday. And then next week, we'll start review Monday, Tuesday, but our test won't be until next Friday. Giving you some extra days to review on them.
I have no idea.
I didn't know that.
You can just do it for that, but if it's a problem where it's asking if there's continuity and show that the graph is continuous at a point, then go through this.
It's not reading. I don't know how to read mine. Yeah, I know. I've got the.